All right, today we're going to talk about finding the area between curves, and it's using integrals, which we are familiar with from last chapter. Example 1 says find the area of the region lying between the curves of y equals x and 2 minus x squared. We can tell from the graph that these cross at 1, 1 and at -2, -2. Now, if it wasn't obvious from the picture, you would have to set those equations equal to each other and solve them for x. So, I know I am going to find the area between these, and we're finding this area using a bunch of tiny little rectangles. And typically, like last chapter when we learned about integrals, we take the integral from the left to the right, so -2 to 1, and it's the left to the right because our rectangles are vertical. We take the top minus the bottom, so 2 minus x squared minus x, and dx, because the thickness of each of our rectangles is an x value. So, now that we know the integral from -2 to 1 of all of this is how we're going to find this area, we can do it. So, we need to antiderive evaluate that from -2 to 1. Now, plug in our 1. We get 2 minus 1/3 minus 1/2. Plug in our -2. We get a -4 minus or plus 8/3 minus 1/2. You simplify all of this, you end up with 9/2 or 4.5. So 9/2 or 4.5. Now, let's try another one. This one says find the area of the region bounded by the graphs of y equals x squared plus 2, which is a parabola that is moved up 2, so you should roughly know what that looks like. Y equals -x, which goes through 0 and has a slope of -1. If you're not sure what these graphs look like, you might need to go back to chapter 1, section 1.2, we learned about some graphs, and 1.3 we learned about some transformations. And they also say from x equals 0, which is a vertical line, and x equals 1. So the area we are needing here is the area in this little chunk that looks kind of like trapezoid, kind of like, trapezoid-like, except it's curved at one end. So we know that our limits of integration are going to be from 0 to 1, because vertical rectangles will give us, well, one of our rectangles in here, vertical rectangles will give us the same top and the same bottom. The top being x squared plus 2, the bottom being -x, so the top minus the bottom, which gives us the integral of x squared plus 2 plus x dx. We have to antiderive 1/3 x cubed plus 2x plus 1/2 x squared from 0 to 1. And when we plug all of these in, plug in a 1, we get 1/3 plus 2 plus 1/2, and minus 0, because 0 plugged into that will give us a 0, and we end up with 2 and 5/6. That's our answer. Now this next one actually gives us a couple regions, and it's nice in the picture. They're labeled for us rather well. We figure out where those graphs intersect, and they intersect at 2, 0 and at -2, -8. But if you notice, we draw a rectangle two integrals, one for the first section, which is this section, and one for the second section. So the integral from -2 to 0 of 3x cubed minus x squared minus 10x plus x squared minus 2x. Let me redo that for you so you know what I'm talking about. Minus -x squared plus 2x dx. We'll take care of the left portion that is enclosed, plus the integral from 0 to 2 of the reverse of -x squared plus 2x minus the 3x cubed minus x squared minus 10x. What I want you to do is take a minute, evaluate these. We'll talk about the answer in class tomorrow. Now finally, sometimes we have an interesting situation where we don't have vertical rectangles. And it's perfectly fine, it works like normal, but we need to graph some things. So if we graph this first equation, y is going to equal x minus 1. So we know that that function has a y-intercept of -1 and a slope of 1. So we end up with this straight line. Sorry, it's not the straightest line we've ever seen. And when we graph the other one, we solve it for y. We get y squared equals 3 minus x. Square rooted y equals positive plus and minus radical 3 minus x. And when you graph both of them, you can make a table, you can do whatever you need to. It looks like, actually I went too far, kind of like a parabola on its side. This is the positive radical 3 minus x, this is the negative radical 3 minus x. So we're talking about the portion in here. Now we could do vertical rectangles, but it would get a little tricky when we get over here at this section because the top and the bottom are the same function, which makes working out an integral very difficult. So an easier way to do this would be to do rectangles on their sides, which means the thickness of these rectangles is now a y value. So our integral is going to have a dy, and our limits of integration need to be y values. So we know that this crosses at -1, -2. We know that this is 2, 1. So we're going y values from the smallest to the biggest. We're going from -2 to 1. From the lowest y value to the biggest y value. And if we're going to take the top minus the bottom, we need to take the right side, because that's our positive x-axis, the right side over here, minus the left side. So the function on the right is that 3 minus y squared. And the function on the left is the y plus 1. Take a second, evaluate that one on your own, and we will talk about the answers to that one and example 3 in class.